Well, good afternoon, everyone. I think it's time that we started again the wonderful conference. So, I'm Chen. I'm from the Universities of Lausanne and Oslo. I have to begin with a disclaimer that I'm a medievalist, but it's a great pleasure and privilege for me to present to you the first speaker of the afternoon session, who is Dr. Saakshi Dulani, who is from the University of Johns Hopkins University of the United States. Dr. Dulani is a postdoctoral fellow in the philosophy and physics departments at Johns Hopkins University. And today, her talk is entitled "The Quantum Past Hypothesis in the Everettian Cosmology." Well, the floor is yours.
Thank you so much. I am so happy that I made it back to Switzerland after several years. I am so happy to be here with you all. My talk today is called "The Quantum Past Hypothesis in Everettian Cosmology," and it's based on joint work with Sean, who will be presenting after me, as well as a PhD student in the physics department, Nadia Diashenko. And this is great news for me, because if you have any questions that I either don't want to answer or can't answer, well, you can bug Sean very soon after. All right. So what I would like to accomplish today is to outline an account of the classical era of time that I would like to generalize to a quantum ontology. And in particular, I'm interested in a formalism where we have unitary evolution. So broadly speaking, I'm going to be basing my analysis on some sort of Everettian cosmology. And in order to motivate how to go about generalizing this account of recovering a thermodynamic arrow, I'm going to offer a proposal for how to stipulate a quantum past hypothesis. And I'm going to offer some details about the nature of entropy that we should be using. And so I will discuss what I think is the most appropriate type, which is quantum Boltzmann entropy. I just want to flag that if any of you are familiar with the work of David Albert and Barry Lower and their former students, Jill North, Eddie Chen, a lot of what I'm saying might seem like it's very aligned with something like the Metaculus or Wentaculus program. I don't explicitly mean to be Humean in that sense, although it's certainly compatible. But I will be Humean in the way David Albert likes us to be Humean, where instead of giving you infinite facts about reality, I will do my best to compress the most interesting ideas in a half an hour, and hopefully you can go home and put that on a clever t-shirt. So, the research question that I want to explore is the following. How does a thermodynamic arrow emerge in a quantum cosmology? And the motivation for this question is to get better at starting with the quantum formalism and recovering some sort of classicality rather than starting classically and then quantizing what you have. As we learned this morning, right, it's very important to distinguish between order of operations when you reverse it, whether it commutes or doesn't commute, and this is one of those instances where it may not commute to start quantum and go classical versus the other way around. In order to tackle this question, I'm going to break it down into parts. So the first part that I want to address is, what do I mean by a thermodynamic arrow? I'm interested in the application of the second law to the universe as a whole, conceived of as a closed system. And there are pervasive phenomena that we are very, that we experience all the time that have what we would call a thermodynamic arrow. For example, a snowman melting over time is a canonical way to understand how heat flows across systems. But there are also a lot of other phenomena that we think depend on the existence of a thermodynamic arrow. So the rise of complexity, life forms like us that drink coffee and then mix cream into coffee, the intricate patterns that form during the mixing process, the rise of disorder like aging, right? So we think that there are extremely crucial aspects of the macroscopic scale that would not, in fact, occur without the existence of an entropic gradient. So now I'm going to give you a brief overview of the classical arrow so that we know what exactly we need to generalize. First, we have the dynamical laws, which are time symmetric. So those alone are not going to give us any sort of arrow of time. The next step is to look at collections of different states that a system can be in and reason statistically about those states. So the idea is that if we want to understand why a snowman melts, right, we say, well, it's very likely that it's going to be more melted in the future than it was in the past. However, we have a problem here because if we want to say that entropy is increasing and that's a manifestation of certain states being more likely, right, so we're going along this curve, then actually any system should start out in its most likely state to begin with, right? It should start out in a maximum entropy state just with minor fluctuations. And once we realize that we have another puzzle, why were we ever out of equilibrium to begin with, then we realize statistical reasoning on its own is not enough. So we need to stipulate that in the past, we started out with very low entropy. And once we add that component, now we can recover this entropic gradient, which is a manifestation of the second law for the universe at large. Eventually, the universe will equilibrate, so we will find ourselves in this region. There's another question of whether there are going to be some pernicious fluctuations that lead to the Boltzmann brain problem. That is something I will leave for Sean to discuss in the next session. But at least we have recovered an error of time in this period here. In that account, I didn't actually define what I meant by entropy, though. So there's a question, what is the appropriate entropy that we must use when talking about the thermodynamic arrow of the universe? One option is to use Gibbs entropy. This is very common, one, because it is convenient to use in calculations. It involves a probability distribution over the system's microstates. And it works very well when we're talking about open systems that are equilibrating spontaneously with each other, or when we are talking about a control theoretic or resource theoretic approach to thermodynamics and statistical mechanics, which is why Gibbs entropy often comes up in discussions about Maxwell's demon, for example. But the problem with Gibbs entropy is that it does not work when we're talking about the entire universe, because as I stipulated in the beginning, I'm conceiving of the entire universe as a closed system. And more importantly, it is conserved under deterministic dynamics. And of course, the second law relies on entropy being able to change over time. So this means that we have to rule out Gibbs entropy, and we have to invoke a different sort of entropy. What is that? Well, Boltzmann entropy seems to be a promising alternative, because what you do is you take the phase space of a system and you partition it into different regions. What region. That will now be the entropy of the system. So what the second law for the universe is saying is that we started out in a microstate within a very low entropy macrostate because the volume of that region was tiny. So this is basically Penrose's thought experiment of what would happen if God tried to randomly locate the region of phase space of our universe's initial condition. Well, the probability of getting there would be extremely, extremely tiny because just of how relatively small the volume of that region is. This works because the partitioning of the phase space means that as you are moving through on a dynamical trajectory, you are entering different regions with different values of entropy, and this also allows for fluctuations into regions of lower entropy, although the amount of time you spend there would be presumably very small. So Boltzmann entropy is the type of entropy that we're going to be most interested in today. And now just to give you a concrete example of what Boltzmann entropy really amounts to. We want to understand where does the coarse-graining procedure come from in the first place, right? What is the basis for how we partition phase space? And an immediate answer is that we're interested in higher level properties of systems that we have empirical access to. So because Claudio is a good friend of a lot of us in this room, and I've shown him a version of this part of the presentation before, I think he would not mind if I use it to demonstrate my point here. For all of you who know Claudio, I think we can safely say that his equilibrium state is to be wearing black, right? That is when he is at his happiest. If he is wearing another color, like red, this would be a very out of equilibrium situation. So how do we understand this in terms of entropy? We have this high-level property, this macro state of wearing black versus wearing red. And what it means for black to be the equilibrium state is that there are just many more ways of instantiating the macro state black. Here, the microstates count as the outfits in Claudio's closet, but there are many fewer ways of instantiating the macro state red. Here, there's only one outfit in this closet that is able to do that. So what Boltzmann entropy does is it establishes a macrostate to microstate correspondence and is essentially an accounting measure. So with that apparatus in mind, now we understand what the statistical second law is really saying. If we have a low entropy initial condition, let's go back to the frozen snowman, it means that there are fewer microstates associated with that macrostate. But over time, it's a numbers game, and it's very likely for the system to evolve into higher entropy macrostates simply because there are more microstates associated with higher entropy macrostates. So this explains why the frozen snowman begins to melt, right? There are more microstates associated with melting, and then it fully melts, and in this case that would be the equilibrium case, that is the macrostate with the maximum number of microstates associated with it. And of course this account is compatible with there being fluctuations because it is possible for your evolution to include microstates along the way that may, temporarily visit lower entropy macrostates, but by a sheer numbers game, that's not going to be very long-lived. So now that I've addressed what I mean by an error of time, I want to explore what is it that I mean by quantum cosmology. So it's a cosmology that, at the very least, got started with what we would call quantum fluctuations, but fluctuation in quantum mechanics is a very loaded word, so this is going to be interpretation dependent, right? Does fluctuation mean collapse? Does fluctuation mean something else? And because I'm interested in unitary quantum mechanics, I'm taking a broadly Everettian view, where fluctuation locally is not going to interfere with global unitarity. So I'm going to tell you a little bit more about how that works. And of course, because now we're in an Everettian framework, it's just too tempting to talk about Schrodinger's cat, not least because there are lots of available illustrations in order to make sense of things. So I gave you the quantum part of what is meant by a quantum cosmology, but that also now informs what is meant by cosmology, right? What do we count as the universe when you have a fundamentally quantum ontology? And it turns out that in an Everettian framework, there are two levels that we have to be mindful of. The first level is the level of the global state. This is going to be perhaps a vector in Hilbert space. We are looking at a finite dimensional Hilbert space for some of the models we'll be discussing today, but it could also be infinite dimensional perhaps. And we have our state evolving unitarily according to the Schrodinger equation. This is a block sphere representation, but similar idea. And then we have an emergent level where we want to get some phenomenology out of the quantum state, right? We care about the development of galaxies, planets, etc. So here, that level of the universe is going to be described by an effective Hamiltonian. And when we ask about how to recover the thermodynamic arrow, now we have to coordinate these two different levels. So I just mentioned that we have an emergent level, but I didn't quite say what I mean by emergence. And that's something that, right, is a huge project. So I'm not going to be able to say too much about it, but ideally, not only do we get thermodynamics out of the quantum state, we also get other temporal asymmetries that seem to either be correlated with the thermodynamic arrow or in some sense dependent on the thermodynamic arrow. That includes our psychological arrow of time, the fact that we feel there's an open future but a fixed past, you know, the arrow in which we find macroscopic records. So there are lots of things that ultimately will hang on the thermodynamic arrow, as I mentioned briefly before. Even though there's so much work to be done in understanding emergence, a good place to start perhaps is with decoherence and branching. So if we decompose the overall Hilbert space into a tensor product between some target system and an environment, and given the talk this morning, maybe it would be more careful for me to say to almost factorize, whatever that means. Then we can talk about at what level we actually have an effective Hamiltonian with respect to the target system. So for simplicity, let's take Schrodinger's cat in a box. And then the environment is anyone opening the box to observe the cat and everything else. So what happens with decoherence is that at first, you have Schrodinger's cat in a superposition between being dead and alive, unfortunately. Maybe we should make this a little more PETA-friendly and say between being asleep and awake. So we have Schrodinger's cat, the target system, in a superposition, and it is in a product state with some environment, right? So they have not interacted yet. But then upon interaction, they become entangled. And what's important is that the environment states are orthogonal. So what that does is it suppresses interference between these different terms, which we're going to now call branches, and suppressing that interference allows for autonomous evolution of each branch with what we would call, you know, a definite state, right? Although the global state is in a superposition, each branch has a definite state of Schrödinger's cat being either dead, unfortunately here, or alive over there. And the environment is going to record the state of the system, so it has to be consistent, right? If we open the box and Schrödinger's cat is dead, then our observations need to accurately record that and match the description. So this is the idea behind decoherence leading to branching. So now we can talk about the thermodynamic arrow not only at the level of the global state, but to recover phenomenology that seems sufficiently classical, we can talk about the thermodynamic arrow along branches as well. So putting all of the parts together, I'm going to return to the question, how does the thermodynamic arrow emerge in a quantum cosmology? Well, it seems like we need to start with a low entropy initial condition that ensures our branching has thermodynamic arrows. And this is going to be now the project for the rest of the talk to really spell out how we go about doing that. So I call it the quantum past hypothesis. And the quantum past hypothesis, like the classical past hypothesis, right, should be able to recover the initial condition, the initial macro state of the universe, that it was in a hot, dense state nearly 14 billion years ago, and then the evolution since then is as we know it. By the way, I think Humeans have their t-shirt. If you don't know that thought experiment by David Albert, the idea is you have an interview with God and you ask, okay, tell me about the universe, but there's not enough time for you to learn an infinite number of facts. So the constraint is it better be able to fit on a t-shirt. And well, here's the t-shirt that the Humeans have been looking for. So when we say that the initial condition of the global state is low entropy, what we're really doing is ensuring that typical branches exhibit an entropic arrow. So we're going to minimize this global entropy, and the evolution is going to be such that when we start branching, they're going to have very low entropy, and on each branch, we're going to have a phenomenologically classical-looking state. And as we increase branching in the future, we get these different branch threads. So we define something called a branch thread, which is a semi-classical history of traversing from one branch to another over time. So we want to also make sure that the entropy of a branch thread exhibits the second law. We start out at low entropy, and entropy increases along any one of these branch threads. We also want to make sure that typical branch threads have this arrow. So how are we going to do that? Well, it's going to depend on, again, how we define entropy. Very commonly for quantum systems, von Neumann entropy is used. This is not surprising because it's a generalization of Gibbs entropy. So what we have here is a probability distribution over different microstates, usually pure states that appear in this density matrix. And von Neumann entropy has similar applications that we discussed before. It can be used for control theory, for example, but it has another uniquely quantum application, which is to quantify the extent of entanglement between open systems. So here we have a little schematic of black hole evaporation. I think you probably guessed by now that that's a case study I'm very passionate about. So if we're looking at this, these entangled modes, and one of these modes in this depiction right here is going to escape as Hawking radiation. If we wanted to describe just the state of this part of the entangled system, we would use a reduced density matrix, and it would have positive von Neumann entropy, indicating that it had some entanglement with an external environment. This, again, is not appropriate for the universe at large. Like I mentioned before, we want to keep conceiving of the universe as a closed system, and if the universe is in a pure state, then the von Neumann entropy is going to be 0. At the very least, it's going to be conserved under unitary evolution. So for similar reasons as before, we're going to be ruling out von Neumann entropy as the right entropy used to recover the thermodynamic arrow. But now there's a question, what is the right entropy? Oh, I didn't do that, okay. What is the right entropy? And this is the basis of our proposal, because we don't think that anyone really has stipulated the right entropy yet. We want the right entropy, like classical Boltzmann entropy, to not depend on whether or not you have an external environment. And we also want to capture macrostate superpositions. So not only are we interested in recovering a classical-looking thermodynamic arrow where you have a frozen snowman melting, right? You want to be able to take into account that now we can be in a superposition of different macrostates because we can be in a superposition of different microstates. So we want our entropy to be able to take into account, for example, that there are different weights here to Schrodinger's cat being dead and alive, and that should be reflected in how we calculate the entropy. So our proposal, which is a pretty novel one in the literature, is called quantum Boltzmann entropy, unsurprisingly, and I'm going to explain how it works, but just as a brief overview, it looks a lot like classical Boltzmann entropy. Instead of partitioning phase space, though, into different regions, now we're going to be partitioning Hilbert space into different subspaces. We're going to replace the volume of phase space with the dimensionality of the Hilbert subspace. We're going to take the logarithm, and then we're going to weight it appropriately with some probability. So what we're suggesting is that this weighted average is going to be the right quantity that we should use to stipulate the quantum path hypothesis, and that in turn will generate the second law for a quantum system. So here we have Penrose's God sticking a pin in Hilbert space and looking at the subspace that contains the universe's state vector. And I want to emphasize that the power of classical Boltzmann entropy lies in the fact that it's a counting measure. So the spirit of that is very much maintained in quantum Boltzmann entropy. So here's what we do. Let's go slowly and first talk about coarse graining. We're going to partition our Hilbert space into different subspaces. So it's going to be decomposed into a direct sum of subspaces HA, let's say. But that, coupled with decoherence, means that we also need to take into account the factorization into the system and environment factors of the Hilbert space. So we're going to further decompose each subspace now into the factors of the target system that is contained within our subspace HA, and then the environment. It is a pretty realistic idealization to say, okay, we have our partitioning and we have our factorization, but we can treat the environment as being common to all of the possible systems of the universe that we care about. So if we're interested in the thermodynamic behavior of galaxies and planets, right, we can treat the environment as being the same on every branch. Now this won't work, let's say, if you have one branch where inflation got going and another branch where inflation didn't get going, but as long as the branches are sufficiently similar that you can trace out an environment that is common to all of the systems of interest, then we can factor it out, and we only really have to worry about the behavior of our target system. So one way to do that is to say everything that has emergent classical behavior is going to be pretty well described by low energy modes. And so on each branch, we're going to treat as the environment the high energy modes. So once we get to this point, let us take the simple example of 3 macrostates of a melting snowman. Right, we have the lowest entropy state, which is the fact that it's frozen, and this corresponds to Hilbert subspace 1, let's call it. A partially melted snowman, which corresponds to subspace 2, and then the fully melted snowman, which corresponds to subspace 3. Because the subspaces differ in their dimensionality, where subspace 1 has the smallest dimensionality, taking the logarithm as its entropy straightforwardly delivers the result that it's going to be smaller than the entropy of subspace 2, right? Because the dimensionality of subspace 2 is bigger, and that's going to be smaller than the dimensionality of subspace 3. So already we can see that we have a thermodynamic arrow looking at just the Boltzmann entropy of the target system. Now we've done a lot of the heavy lifting, so we can quite straightforwardly at this point figure out what the entropy of a branch is. So classically, we just think of it as in one world, right? We have this arrow, but what's going on here is that we're really evolving along a branch thread where on branch 1, let's say, on one branch earlier in time, we have macrostate 1, and then on another branch later in time, we have macrostate 2, and then on yet another branch at a later time, we have macrostate 3. So in order to calculate the entropies of these individual branches, we now have to take into account the environment degrees of freedom, because our Hilbert space partitioning said that the entire subspace HA counts as a quantum macrostate. But this is not too difficult. All we have to do is take the logarithm of the dimensionality of that factor and add it up. And that basically gives us the quantum Boltzmann entropy of the branch. So as you can see, we have, again, the thermodynamic arrow where we go from low entropy to high entropy because the thermodynamic contribution is coming from the target system. By design, the entropy of the environment is going to be constant. Now here comes the fun part. The story given now sits well with our intuitions about our experience of the thermodynamic arrow because we only ever are on a given branch thread. However, if you look at the global state, you'll realize that actually you can be in a superposition of all of these macrostates at one time. And so we also need to understand on that level what we mean by the second law. So if we now expand out the global state such that we have the product state between the target system and the environment, and we also include the amplitudes, what we realize is that each component of the superposition has a microstate, which is this product state, that is contained within a macrostate. It's contained within a particular Hilbert subspace. And now we want to weight the contribution of each of these components and see how that affects the overall entropy. So what do? We project onto the Hilbert subspace of interest with an operator, and we calculate the probability, which basically is the Born rule. For any of these components that are in some subspace A, right, we just simply take the sum of their Born probabilities, and that's going to be the entropic contribution of macrostate A. So in this simple example, right, we're going to have a weighted average where we take the probability of our lowest entropy macrostate, somewhere in the middle, and then our maximum entropy macro state, and that is the quantity that we assign to the global state, and that is also a quantity that we track when we want to recover the second law. So with all of that machinery under our belt, now we can precisely define what the quantum past hypothesis is supposed to be. It is minimizing the global quantum Boltzmann entropy. How do you do that? Well, you set the probability of being in the lowest entropy macro state to 1. What that means is that all of your branches start out in the lowest entropy macro state. You can relax this condition, so you can just make the probability almost 1, and that means that most of your branches will start out in the lowest entropy condition, but in our simulations, we made it exactly 1. And then over time, the probability distribution will evolve, as long as we're not in the energy basis. So as the probability distribution evolves, we have very similar statistical reasoning as we did in the classical case. It's just very likely for different components of the global state to end up in progressively higher macro states simply because those subspaces are larger, right? And then eventually we're going to get to a place where our probability distribution is now concentrated in the maximum entropy macro state. So our snowman, right, on most branches is going to be fully melted. It's important to note, though, an interesting difference between what is meant by equilibrium with quantum Boltzmann entropy and classical Boltzmann entropy. The probability of being in the maximum entropy state is not quite 1, although it's almost 1. That is because the superposition is conserved under unitary evolution. So it will always be sampling lower entropy macro states, but the weights are obviously going to be minuscule compared to the weight of the highest entropy macro state. So that means that our equilibrium entropy is going to be almost, but not quite, the value of the maximum entropy. And now, to give you some food for thought, there are several advantages to defining quantum Boltzmann entropy in this way. One, there's a pretty clean correspondence between the quantum Boltzmann entropy of a branch and the classical Boltzmann entropy of that branch, because the reason we said that Hilbert space dimensionality is analogous to phase-space volume is that every classical microstate now becomes an eigenstate in Hilbert space. And if you look at a proposal by Landauer and Lipschitz, then the idea is that if phase-space volume is related to Hilbert space dimensionality by this proportionality factor right here, which is Planck's constant raised to 3n, and particles, let's say, in 3 dimensions, then now we can use this relation to calculate the classical Boltzmann entropy from the quantum Boltzmann entropy. Another advantage of quantum Boltzmann entropy is that it goes up because we have a foray into higher entropy macro states. It doesn't go up simply with branching. So this is a very nice way to differentiate the thermodynamic arrow from other arrows that especially come up in quantum mechanics, like the entanglement and decoherence arrow. So if you think of Schrodinger's cat, and I can go back to that if anyone has any questions, calculating the weighted average is going to be the same whether your system and your environment are in a product state or whether you have decohered, because what you're doing is you're using the same Born probabilities. And as long as the time interval is sufficiently small such that the state has not gotten a chance to move into different subspaces, the entropy before and after are going to be almost the same. And this is a feature, because there's a lot of discussion in the literature that tries to equivocate between entanglement entropy and thermodynamic entropy, and this is a very conceptually clean way of keeping them distinct. And then finally, this is something I'd be happy to answer in Q&A, but no existing proposal of quantum thermodynamic entropy, we believe, works for an Everettian cosmology. So here are some of the proposals that we've looked at and we've modified. There's something called coarse-grained thermal entropy, which basically simulates a closed system as a bunch of open systems and looks at their entanglement entropies. But this is going to go up monotonically, it can't fluctuate, and it's just conceptually different because this quantity will go up with branching, even if there wasn't enough time to really meaningfully change the system's macro state. There's another proposal called observational entropy. If you notice, it has this term that looks exactly like our definition, but it has another term that is Gibbsian in nature. So this is more operational, it's concerned with measurement uncertainty. And then finally, there's a quantum Boltzmann entropy operator, which can be used to derive our equation. It's just the expectation value of what's going on here. And this proposal was made because of skepticism for long-lived macrostate superpositions, but in an Everettian framework, that obviously is a central feature. So all of this is discussed in our paper, and I encourage you to take a look when you have time. So thank you.
Thank you very much for this inspiring talk. So first of all, I think we will have to invite our dear Maria to give the comments.
Oh, okay, thanks. Okay, thanks. Okay, yes, I have prepared a couple of comments and questions that I've tried to gather into sort of 3 different categories. Okay, that's not what I expected. Oh, it doesn't quite. Okay. So the first sort of question I have relates to this idea of quantum macrostates and how we're supposed to think about this. So this is the quantum Boltzmann entropy definition that you end up giving and you just presented. And if I understood it correctly, it's the idea that we take a Hubble space, divide it into these subsectors that each are supposed to correspond to a macrostate, every sector, and then all the microstates are somehow corresponding to that macrostate is within that sector. And then the greater the dimensionality of the specific sector, the greater the entropy related to that quantum macrostate. Yes, and typically when we talk about the relationship between micro and macrostates, so as in the classical case here, we just have some particles in a box. There are 4 possible macrostates I just sketched here, and a lot more, well, there are 8 microstates corresponding to these mapping onto it. So here, when we want to talk about how we sort of put together the microstates to account for the macrostates, I sort of have a clear ontological picture going on. I have particles, I have some configurations within it. But when I think about the quantum macrostates, it's a little bit more unclear to me how am I supposed to think about what is actually represented by this quantum macrostate. And so this is sort of my first question, is sort of which macrostates are we supposed to think are actually associated with these sectors in Hilbert space. And I think the most natural reading would be that, of course, the entropy, or sort of the macrostate that we're talking about, is actually at the emergent level. So whatever is happening at the branch level, there's a well that has a certain entropy, and if it has a certain entropy, then it maps onto that sector of Hilbert space. But it seems that this cannot be the only way that we want to think about it, because this seems to be at the emergent level. Now we want to talk about fundamental entropy. So if we need to sort of refer to the emergent entropy level and ontology in order to understand why we partition our Hilbert space as we do, there seems to be some sort of circularity going on where we, in order to even sector Hilbert space into these macrostates, we need to have an eye on the emergent worlds, and then only once we have entropy in the emergent worlds can we define the sectors, and then we can use this more fundamental entropy notion to then afterwards recover entropy in the emergent worlds. So there seems to be something going on here. And of course, it's normal that we need a macro level and a micro level, and we cannot really make sense of entropy without also referring to the macro level. But here there seems to be also an additional layer of not just macro and micro, but also emergent level that we need to. So sort of the first question is sort of what are precisely the macro and micro states in the quantum case? How am I supposed to think about it? And how exactly do these relate to the emergent classical micro and macro states? So this is my first question. Then the second question sort of relates to how I'm supposed to understand as well the fundamental second law. So the classical Boltzmann entropy measures the multiplicity of microstates for a given microstate, or at least the volume of phase split related to this. And it's exactly this that underwrites the second law. So usually we have some sort of macrostate, and then microstates that come up onto it, and the more microstates we have, the greater our volume, and therefore also probability for it. And here I get a bit, I'm struggling a bit to understand because we're having an Everettian sort of background going on. So it seems that in Everettian quantum mechanics, I suppose this is one question, all the branches are somehow actualized. And if this means that the branches sort of correspond, I guess that's a question, do the branches correspond to the quantum microstates somehow, such that all the quantum microstates are actualized? And in that case, I'm not really sure what it means that entropy increases over time. In sort of this Everettian picture, of course, towards the end of the talk, you talk about how we can sort of talk about the weighting of sort of some of the branches being greater than the others. So the branches with the greatest entropy sort of have a greater weight as time goes on. And this is how we're supposed to understand the second law. But at the end of the day, what we really have at the more fundamental level is just this vector in Hilbert space that's evolving, and it's not really clear how I'm supposed to think about this. So my question is sort of why should the dominance of high entropy branches explain the fundamental second law rather than merely describe the distribution of branches within the universal wave function? Why is this really an analog of the second law and not just saying something about entropy at the emergent level? That's not quite clear to me. And then my final question relates to the environment, sort of clarificatory. So we need this sort of environment in order to get the decoherence and the emerging branches. And you talk about how we have this environment that at least for a lot of the branches can be a common factor that we can sort of trace out over. And that this needs to have some sort of stable entropy, so to be at some sort of thermal equilibrium. And since we have emergent universes, I'm wondering what this environment exactly is supposed to be that can be common to all. So I guess here, what can be common to all subsystems, so all universes, and can have constant entropy? Is it something that's supposed to be external to the universe? Or can we think about it as a part of it, or how to think about it? And then also, if we need to have something that is in this environment that is in thermal equilibrium, and it needs to be there right from the beginning when we have our branching, it seems that if we have a part, at least that is not in the lowest possible entropy state, but at equilibrium, is it really the case then that the initial state truly starts to a probability 1 in the lowest entropy sector, if we need to have some degrees of freedom that are already at equilibrium? And maybe that's not a problem, but what are the consequences if we don't have probability 1, strictly speaking, for being in the lowest entropy sector for the environment? So those are my 3 questions.
Okay, so I know everyone has been trying to answer all of the questions brought up by the commentator. Hopefully I will get to all of the questions over the course of our discussion. but I am going to prioritize the ones that I find very compelling. Here we go. Where was the one with the circularity? Oh yes, the circularity of explanation. So if I understood correctly, the worry was that we are already relying on a classical description to define macrostates and emergence in the first place. So are we really starting from a quantum first formalism, or are we basically, putting in what we want to get out, which is the classical looking behavior? This is a question that also occurred to me, not for the quantum case, but just about the story that is given for an account like the metaculus, that basically you give me the three components that I mentioned, the laws, the statistical properties, and the low entropy macrostate, and now I recover everything that I want about the macroscopic universe. Someone like Barry Lower would call it the probability map. That's what the metaculus means, by the way. It's a reference to a movie. I asked this question to Heather Douglas, and she said that in her view, it's epistemologically circular because coarse graining is not so innocent of a move. There's a lot built into it, but that ontologically it's not circular. And maybe what I can say in this case, and perhaps Sean has more to say about it, is that when we do make our choices for how to partition the Hilbert space and how to factorize into system and environment, it is often done with an eye looking forward about what is the appropriate cuts that are going to get us the classical behavior that we're looking for. But I think what's important, one, is that dynamically we're starting from a quantum first place, so all of the infrastructure that is being used is looking at quantum states, not classical states at the micro level. But I do agree that there is this uncomfortable circularity that is explaining the emergent phenomena. And I want to point out that I was very careful. I always used the term emerge or emergence. I said nothing about its relationship to reduction. And there are lots of thoughts on what the relationship is between emergence and reduction. I'm working on a project where I want to argue that this sort of account, even in classical thermodynamics, is non-reductionist. And so I would then say, based on that there is no such thing as fundamental entropy. Like, you all already have to appeal to emergence to basically define your maps between microstates and macrostates, and entropy is an emergent level property. I would not say that it's a fundamental property. Okay, and then so this was an interesting question. I'm not sure if I understood more than what is written at face value, but just to clarify, the temporal aspect of the branches having different entropy is really in the relative proportion. So the idea is, in the beginning, if your probability distribution is concentrated in the lowest entropy macrostate, and then later it shifts to the highest entropy macrostate, your distribution of what macrostates your branches are in is going to change. And then when you look at any typical branch thread, so typicality is really important, and why we insisted on having the weighted average. You need a measure over branches at every moment in time to be able to reconstruct these temporal branch threads. and see how entropy is changing from one branch to another at different times. So I think they're very interrelated. And the importance of typicality is that for explanatory power, you don't want to say that, oh, maybe you started out in a global state where a very small fraction of your branches have low entropy, all the others were already in the highest entropy state. That has low predictive power because now it's atypical for you to find yourself on a branch that has the second arrow. So that's the connection between the temporal evolution and, I guess, the more synchronic distribution of branches. And then what plays the role of the environment, and why would they have constant entropy? So because this proposal takes seriously that the universe is a closed system, the environment certainly does not mean that there's something external to that. But I do see the question mark about what kind of environment would have constant entropy that is the same for all of your target systems. I am not quite sure, but the closest analogy I can think of is if you have some sort of bath, right, that is pretty much stable and your target system is equilibrating with that bath. Maybe that is plausible if we think about the target system as being described by low energy modes and our bath being described by very high energy modes. But another conceptual sort of subtlety about our account is because decoherence requires on the system environment cut, we are only interested in the thermodynamic macrostate of the target system. The only part of the macrostate that we're interested in for the environment is that it records the state consistently of the system. So really its degrees of freedom come along for the ride. But because the branch itself, the product state, because each branch is in a product state between the system and the environment, that lives in our Hilbert subspace HA, right? We have to make sure we include all of those degrees of freedom. And then, what are the consequences if the environment is not in the lowest entropy state that it could be in? Because it comes along for the ride and it's constant, there's no sense in which it's low entropy versus high entropy, right, in this simplified situation. So really, when we're talking about minimizing our global quantum Boltzmann entropy, that's going to affect the macro state of the target system that we interpret as being properly thermodynamic. Now, like I said, it was an easy but pretty rigid initial condition to say that the probability of being in the lowest entropy macro state is 1. You can certainly relax that. The issue is that the more you relax it, right, the more you allow for branch threads to have behavior that deviates from the second law. But certainly to say that it's still typical that most branches start out in the lowest entropy sector would be sufficient for our purposes. So thank you for your comments.
Thanks for the talk. It's really interesting. I have 2 different questions, and I won't try to ask all of them now here because there are other people. But let's start with 2, maybe.
Okay.
I thought that during the talk I had spotted what would be the quantum path hypothesis.
Okay.
And it wasn't quite what I expected.
Oh, interesting.
And I say that because I guess you know, like when Boltzmann thought he had derived the second law, it was because tacitly he had this assumption about molecular chaos that the velocities were not actually correlated because they are like a product state.
Yeah.
And at some point in your slides, you did write a product state, which was between the system and environment at an initial state. And so I was wondering, is that also kind of like form of a sort of like quantum path hypothesis that you pick this particular uncorrelated state and you start from there?
Yes, so it is a quantum past hypothesis, but not for the thermodynamic arrow. I think that would be the past hypothesis for an entanglement or decoherence arrow, which is how you factorize your Hilbert space. And your initial state basically has right, is like pre-entanglement in a way, and then as your subsystems interact, they become more and more entangled, and that leads to a proliferation of branches. So I'm glad you asked that, because I think there is also this, this desire to unify these different options for entropy for quantum systems. Like, how great would it be if we could just say that entanglement entropy is really thermodynamic entropy because there's some intricate connection between the two? But based on this proposal, that would be a quantum test hypothesis for a different era. Yeah.
Maybe the second question has to do with, so as you know, like, you can go from Gibbs entropy to Boltzmann entropy, depending on the state that you choose, right?
Right.
And here, I wonder if actually something similar maybe is happening under the hood, in the sense that you could think about an entropy with a particular state. And it turns out that people also have, I mean, there is a particular state that actually gives you more or less the kind of entropy that you arrive, which is in the context of now a K of T, like what we call a K-mass state, which is a state that's a full rank state. It's a nicely mixed state. So it's the analog of the state that brings you from the Gibbs entropy to the Boltzmann entropy. And of course, people are using those things when people talk about modular flow, all the way back to this paper by Rovelli and Combs about how to find time from this modular evolution that is intrinsic to the algebras. So I was wondering if you guys have thought about that, if there is any particular connection. Because it seems to me, I mean, from afar, that maybe what you're trying to define as a quantum Boltzmann entropy might actually be kind of like the modular, the analog, what would be the modular entropy for a particular state.
Okay, so I'm not familiar with the definition that you just brought up, but I can say this. It is true that Gibbs entropy seems to reduce to Boltzmann entropy for the microcanonical ensemble, which is used for closed systems, and each microstate is equiprobable. And in fact, you could also make Gibbs entropy work, like you could get around the issue that it's conserved under deterministic dynamics if you, at different time intervals, coarse grain the probability distribution. So basically, you're throwing away information about your microstates. There is this whole debate in philosophy of physics whether that captures the error of time, because that seems to be based on right, a subject's level of knowledge or uncertainty about the system. I am not convinced by the shape that debate has taken. I think both entropies can be given subjective interpretations. I think it also somewhat depends on how you interpret probability to say what's the interpretation of probability in Gibbs entropy. But based on discussions that I've had with Sean, what I do find more convincing is that if you are throwing away information for Gibbs entropy, or you're just coarse graining your probability distribution, and that will then coincide or agree with what you would get with a Boltzmannian approach, then you're probably doing that on the basis of macrostates. So it seems like macrostates are more foundational, and any coarse graining procedure you choose for Gibbs entropy or perhaps even von Neumann entropy is going to be based somehow on the Boltzmannian idea of macrostates. And so, yeah, if there's something similar going on with von Neumann entropy, that sometimes it'll agree with quantum Boltzmann entropy, I would just say, you know, sure, do whatever works practically, absolutely. Like we had to use numerical simulations to work with quantum Boltzmann entropy, but philosophically, I think the idea of macrostate is what's doing a lot of the heavy lifting, and why this is just, in a way, it's riding the coattails of quantum Boltzmann. Oh, yes.
Yeah, so I think we had a little bit of that discussion before. Let me know if I should ask Sean, but you also said you have opinions about whether we should take those different measures to be able to also have a subjective interpretation. And I was wondering exactly on the motivation for you guys. You did mention explicitly that you want to have the universe as a closed system. That was one part of the motivation. You also want some sort of frequentist or sort of interpretation of the, in terms of volume of microstates. So you want to have this concept of time that is definable all throughout the universe with the branching. I was wondering if there's anything in that project that sort of counters the will to have sort of the true monotonicity of time in terms of only like Bayesian credences, that you could only rationally assume, you could only like reliably extract work if you assume the monotonicity, and when it is
Monotonicity of what, sorry?
the monotonicity of entropy.
Okay, yeah.
And I'm just wondering that because I'm more familiar, but because when I think of entropy in a Everettian picture, I think of decision theory, like making decisions in terms of in what branch am I likely to find myself in the future, and that seems like to match so well that I would personally tend to that. So I'm wondering what is like the ultimate, goal of defining time in that sort of more ontic and frequentist view.
Defining time or defining entropy?
Sorry, the arrow of time. In
The
terms
arrow
of
of
that
time.
and entropy, yeah.
Yeah, so I think Sean would be well positioned to answer this because he subscribes both to self-locating uncertainty and the objectivity of the arrow of time.
Okay.
But one thing I can say is that the Born measure over branches, I think, can be made very compatible with this Bayesian attitude about which branch will I find myself in. At any given time, the Born measure will say what branch am I in now, but with the quantum past hypothesis and the statistical reasoning, knowing that also will give you information about what kind of branch will I be in the future, because what we want to make typical is that entropy increases over the course of a branch thread. So maybe I'm not necessarily seeing the incompatibility with using decision theory in order to make inferences about whether or not we will experience an arrow of time. But if you want to use entropy for the purpose of control and extracting work, then I think you are just doing something different with thermodynamics. Like, then it's just we veered from talking about the arrow of time to something else.
Yeah, so I think the only sort of motivation for me, I completely agree with you that the whole picture, you can go from one interpretation to the other. You just have to consistently define your concepts and your measures. I'm just wondering, like, what the conceptual matching is with the target of having the arrow of time, because usually you'd expect, if you think there's something ontologically fixed about monotonicity of time. If you want monotonicity, then you want the actual measure that gives you the monotonicity rather than the one that allows fluctuations, that sort of thing. But I'm happy to reflect and do it again after Sean.
Sure, I'll take one last shot at it. We don't expect monotonicity with quantum Boltzmann entropy, though, right? Like with classical Boltzmann entropy. That was one of the advantages.
Exactly.
Yeah.
But then why would you say that this is a good characterization of the arrow of time? I mean,
so I think there's a very rich legacy for why we abandoned monotonicity for the arrow of time. It's because it seems like if you even allow for Poincaré recurrence, then you are going to get arbitrarily close back to your initial condition. So the second the second law comes with an asterisk, right? It's on timescales that are long enough where we don't really see pathological or anti-thermodynamic behavior, but short enough that it's much shorter than the Poincaré recurrence time, because according to recurrence, right, you will dip very low in entropy, much like your initial condition.
So thanks. So I have a question about the epistemology versus ontology thing. Sort of in the realm of like the circularity theory, but I'm just really trying to understand this. So it's fair to say something's epistemologically circular as long as it's not ontologically circular when you're giving an ontological account of something.
Right.
And what I wanted to, in your definition of coarse graining, part of the definition was that you do the same environment, more or less. Okay.
I mean, it doesn't have to be that way, but that was the simpler scenario that we looked at. Yeah.
Maybe what I'm asking is, what exactly does the definition require? Because the worry is, or at least I'd like to hear more about, if it's part of the ontological account that you're giving, that there's something that has to correspond to the same environment, then epistemological circularity is not the worry. Then it's, again, like you need to define that to, in a way that's not going to get you involved in any kind of circularity. And to follow up, maybe then that additional definition sounds like it actually might be like a supplement to the past hypothesis. So like the simpler, in the classical case, like the past hypothesis, that's the kind of objection that people would raise. Like, what's the justification for the past hypothesis? And it's, well, maybe it's epistemologically circular, to have this experience, but ontologically we need it. And we take it, right, so it's part of the ontological story. So what I'm trying to get a sense of here is what's going on and what exactly is the relationship.
Yeah, so this was a scenario that we thought was plausible for the kinds of phenomenology that we want to describe, but it is certainly not required. I mean, you could stop right here, where you do have, right, where you're not factoring out this environment term, right, that's going to be branch specific, and then you would care about the entropy change of the environment as well. So like its macro state would be changing. I mean, it's just it's a more complex situation to deal with, but our definition certainly can handle it, where all you would do now is over here, right, you would include both of these terms in the branch entropy, and this term won't be constant anymore. So that was a choice. That was just a certain modeling choice where we're like, as an idealization, let's take the environment as good as the same. Like in the snowman situation, for example, it's like our target system is the snowman, and we're going to take mostly everything. We're going to idealize the environment around the snowman to be the same across branches. So we're not really focusing on how its macro state is changing. But I would say this is, maybe I'm not really understanding how this is connected to the circularity question.
It's not the same objection.
Yeah.
The thought is that, like, you have it, okay, so as I was understanding it, if part of the definition involves same environment or some equivalent, then you've got to do that ontologically. Maybe epistemologically we can't find anything without circularity, but you've got to have a non-circular ontological definition. And maybe a way to get, so I was just trying to understand exactly why, and one way to get that is to add another postulate, just like Albert did with the past hypothesis. So then you would have a richer kind of, in some sense you can see there's a richer past hypothesis or a more complex one, maybe there's just a second postulate. Just trying to understand how you want to go and what you do.
I see. Yeah, I'll have to think about whether this stipulation right here is something that would be folded into the past hypothesis, but I should have said in my presentation that I'm actually not taking a stance on the status of the past hypothesis, right? It could be a brute fact, it could be right, a law of nature, of the Humean variety, or it could be clues that invite us to new physics. I mean, we're sympathetic to that last option. But yeah, I would say my worry about specifying this ontologically.
I think it's not even true. I think that's a useful simplification for the toy
Okay, that's
example.
super helpful. Okay,
Yeah.
that's super helpful.
The environment is not the same before the QCD phase transition as it is after. So
No, sorry, it's not the same. Okay, that's where the clarification is required. When I say same environment, I mean same across all branches after decoherence. So it very much changes before and after decoherence, because if we think of Schrodinger's cat, the environment has to properly measure the state of the
That's
cat.
why I think you need sameness in environment that is just not, that's not going to be circular, but there's still something to define in there.
Sure, yeah, same environment here is just what allows us to take this out of these brackets and basically, right, say that this is not going to sensitively depend on which subspace we're in.
Thanks.
Okay, I think we have run out of time, but I suggest that we continue the conversation over a cup of tea or coffee before we convene here in a portion that is 3 o'clock sharp. Let's thank our speaker again.